Preparing for a Backend Engineering at DigitalOcean interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a reliable REST API for creating and managing cloud droplets? I would model droplets as resources with endpoints such as post droplets, get droplets, id, and delete droplets, id. Creation should validate region, image, size, and SSH keys, then return 202 with an operation identifier because provisioning is asynchronous. I would enforce authentication, authorization, idempotency keys, pagination, rate limits, and versioned contracts. A durable job queue would process provisioning, while status endpoints and webhooks expose progress. Metrics, tracing, and structured errors complete the design. While answering, cover resource modeling, HTTP verbs and status codes, authentication, validation, pagination, idempotency, asynchronous provisioning, rate limits, versioning, observability, and clear error responses suitable for both customers and internal tooling. Question 2. What techniques would you use to make a backend service highly available across regions? High availability starts by eliminating single failure domains, deploy stateless instances across zones, replicate data, and use health-aware load balancing. For multi-region service, I would choose active-active only when conflict handling and replication lag are acceptable. Otherwise, active-passive simplifies writes and failover. Define RTO and RPO before selecting architecture. Automated health checks, tested failover, backups, capacity headroom, and graceful degradation matter more than simply adding replicas. Every dependency needs an explicit failure strategy. Make sure to cover failure domains, multi-zone deployment, regional isolation, health checks, traffic routing, replication, failover decisions, consistency expectations, disaster recovery objectives, graceful degradation, and the operational cost of active-active versus active-passive architectures. Question 3. How would you implement idempotency for an API that provisions infrastructure? I would require an idempotency key for every provisioning request. The service stores that key with a request fingerprint, initial status, and resulting resource or operation identifier in durable storage. A repeated request returns the original response rather than creating another resource. A different payload using the same key is rejected. The reservation must be atomic, usually through a unique database constraint. I would retain records long enough for realistic retries and document expiration behavior. In your answer, talk about client-generated keys, request fingerprints, durable storage, replayed responses, state transitions, concurrent requests, expiration policies, failure recovery, and why idempotency is essential when clients retry network failures. Question 4. How do database indexes affect backend performance, and how would you choose them? An index accelerates reads by avoiding full scans, but it consumes storage and makes inserts, updates, and deletes more expensive. I begin with actual query patterns, inspect execution plans, and index selective filter or join columns. Composite indexes should follow the query's equality, range, and ordering needs. Column order matters. Covering indexes can reduce table lookups, though they increase size. I validate improvements with production-like benchmarks and remove unused indexes during controlled migrations. Be sure to mention query patterns, selectivity, composite index ordering, covering indexes, write amplification, storage cost, execution plans, cardinality, migrations, and measuring real workload performance instead of indexing every column. Question 5. How would you handle database schema migrations for a continuously running production service? I use an expand and contract approach. First, add nullable or optional structures without breaking the current application. Next, deploy code that can read both formats and dual write when necessary, then backfill in throttled batches. After verifying consistency, switch reads, enforce constraints, and remove legacy fields in a later release. I avoid long blocking locks, monitor replication lag and error rates, and design rollback steps before execution. Migration tooling should be repeatable and observable. Focus on backward-compatible changes, expand and contract migration, dual reads or writes, deployment ordering, backfills, locking risks, rollback plans, feature flags, monitoring, and safe handling of large tables with minimal customer impact. Question 6. When would you choose a message queue over synchronous service-to-service communication? I choose a queue when work is slow, bursty, or can complete asynchronously, such as image processing or droplet provisioning. Queues absorb spikes, decouple services, and enable controlled retries, but they introduce eventual consistency and operational complexity. Consumers must be idempotent because at least once delivery is common. I define ordering requirements, visibility timeouts, dead letter handling, and backpressure limits. For a small, latency-sensitive lookup where the caller needs an immediate result, synchronous communication is clearer. Make sure to cover latency, coupling, workload spikes, retries, ordering, delivery guarantees, backpressure, dead letter queues, idempotent consumers, user-facing expectations, and cases where synchronous responses remain simpler and preferable. Question 7. How would you diagnose a sudden increase in API latency? I would first confirm the scope using P50, P95, and P99 latency by endpoint, region, and status code. Then I would correlate the change with deployments, traffic, resource saturation, database execution plans, queue depth, and downstream timing. Distributed traces help identify whether time is spent in application code or dependencies. I would mitigate quickly through rollback, traffic shifting, caching, or capacity changes, then reproduce the cause, add a regression test, and document the incident. In your answer, discuss latency percentiles, dashboards, distributed tracing, recent deployments, saturation signals, database plans, dependency timing, queue depth, traffic changes, targeted experiments, and separating customer impact from internal symptoms. Question 8. What does good observability look like for a backend service? Good observability connects metrics, structured logs, and distributed traces around a request or operation identifier. I would track request rate, errors, latency percentiles, saturation, queue depth, and dependency health, then define service-level objectives for important user journeys. Logs should include structured context without secrets, while trace sampling must control cost and cardinality. Alerts should indicate actionable symptoms rather than every exception. Dashboards should support both rapid incident triage and longer-term capacity planning. Cover the 3 pillars of metrics, logs, and traces: structured context, correlation identifiers, service-level indicators, alert quality, cardinality control, dashboards, privacy, and how observability supports debugging without overwhelming engineers. Question 9. How would you design authentication and authorization for a cloud management API? I would separate authentication from authorization. Authentication could use short-lived tokens or scoped API keys, stored and transmitted securely, with rotation and revocation support. Authorization should evaluate the caller, action, resource, and tenant, following least privilege through roles or explicit policies. Sensitive operations may require stronger confirmation or step-up authentication. Every decision and administrative change needs an auditable record. I would centralize policy evaluation, test deny cases, and never trust client-supplied ownership fields. Discuss identity verification, API tokens, short-lived credentials, role-based or resource-based permissions, least privilege, token rotation, secret storage, audit logging, revocation, tenant isolation, and secure handling of administrative actions. Question 10. How would you prevent noisy neighbors in a multi-tenant backend platform? I would enforce tenant-aware quotas for requests, CPU, memory, storage, and concurrent operations, with separate controls for expensive endpoints. A fair scheduler can prevent one customer from consuming all workers, while rate limiting protects shared dependencies. Per-tenant metrics reveal abuse and capacity trends, Resource pools or dedicated workers can isolate especially demanding workloads. Limits should produce clear errors and support approved increases. The design must preserve fairness without wasting capacity, so quotas should be measurable and adjustable. Be sure to mention quotas, rate limiting, concurrency controls, workload isolation, fair scheduling, per-tenant metrics, noisy neighbor detection, resource pools, priority policies, and balancing tenant fairness against overall infrastructure utilization. Question 11. Explain caching strategy for a backend service that serves frequently requested cloud metadata. For metadata that changes less frequently than it is read, I would use cache aside, read from cache, fetch from the database on a miss, then populate with a bounded TTL. Updates should invalidate affected keys or publish invalidation events. I would prevent stampedes with request coalescing or jittered expiration and use negative caching carefully. Cache failures must fall back safely to the database with protection against overload. Metrics should include hit rate, stale responses, evictions, and backend load. Focus on cacheability, invalidation, TTLs, consistency requirements, cache aside or write-through patterns, stampede prevention, negative caching, distributed cache failures, key design, tenant isolation, and measuring hit rate and freshness. Question 12. What is your approach to retries and timeouts between backend services? Every remote call needs a deadline aligned with the user request, not an unlimited timeout. I retry only transient failures, using bounded exponential backoff with jitter and a small retry budget. The operation must be idempotent or protected by an idempotency key. Circuit breakers or adaptive shedding prevent unhealthy dependencies from causing cascading failure. I propagate deadlines through calls and measure retry volume, because retries can multiply load. Permanent validation errors should fail immediately rather than being retried. In your answer, cover bounded timeouts, exponential backoff with jitter, retry budgets, transient versus permanent errors, idempotency, circuit breakers, deadlines, load amplification, and coordinated policies across service boundaries. Question 13. How would you design a background job system for long-running infrastructure operations? I would represent each operation as a durable state machine, such as queued, running, succeeded, failed, or cancelled. A queue dispatches jobs to workers using leases or visibility timeouts, so abandoned work becomes retriable. Workers must make each step idempotent and persist checkpoints where practical. Exponential backoff handles transient failures, while permanent failures go to a dead letter workflow. The API returns an operation ID, and clients can poll or subscribe to progress. Metrics expose age, throughput, retries, and stuck jobs. Discuss durable queues, job state machines, worker leases, visibility timeouts, retries, cancellation, progress reporting, idempotent execution, dead letter handling, scheduling, and recovery after worker or process failure. Question 14. How would you ensure consistency when updating multiple services during a customer operation? I would avoid pretending that independent databases support one atomic transaction. Instead, I would use a saga. Each service commits its local change and emits an event, while an orchestrator tracks progress and invokes compensating actions when later steps fail. The transactional outbox keeps database changes and events consistent. Consumers must be idempotent and tolerate duplicates or reordering. User-facing status should distinguish pending, partially completed, failed, and recovered states. Reconciliation jobs repair rare inconsistencies. Make sure to cover distributed transaction limitations, saga orchestration, compensating actions, transactional outbox, event ordering, idempotent consumers, partial failure, reconciliation, and explicit user-visible operation states. Question 15. How would you safely roll out a significant backend change? I would separate code deployment from feature activation with a flag. After automated tests and compatibility checks, I would deploy to a small canary population, compare error rate, latency, resource use, and business metrics against baseline, then expand gradually. Database changes must support both old and new application versions during overlap. I would define rollback thresholds beforehand and keep rollback simple. Flags need ownership, expiration dates, auditability, and a tested emergency path rather than becoming permanent complexity. Discuss small increments, feature flags, backward compatibility, canary or blue-green deployment, automated tests, health signals, rollback criteria, database compatibility, traffic percentages, and communicating operational ownership during rollout. Question 16. How would you design rate limiting for public APIs used by many tenants? I would use token buckets keyed by tenant, credential, endpoint, and sometimes source network. The bucket defines a sustainable rate while allowing controlled bursts. For multiple API instances, counters need a shared low-latency store or a carefully designed local plus global approach. Responses should communicate limits and retry timing, typically with 429 status. Different operations deserve different costs, and approved internal traffic still needs safeguards. I would monitor rejected requests, legitimate throttling, abuse patterns, and limiter availability. Cover tenant and endpoint dimensions, token bucket or leaky bucket algorithms, distributed coordination, burst allowance, fairness, response headers, rejected requests, trusted internal traffic, configuration changes, and monitoring limit effectiveness. Question 17. What testing strategy would you use for a backend service that manages customer infrastructure? I use a testing pyramid, fast unit tests for business rules, integration tests for databases and queues, contract tests for service boundaries, and a small number of end-to-end workflows. Infrastructure operations also need concurrency, timeout, retry, permission, migration, and failure injection tests. Load tests validate capacity and tail latency with realistic tenant behavior. Tests should use isolated fixtures, deterministic clocks where possible, and ephemeral dependencies. Production monitoring remains essential because no test suite models every failure. In your answer, include unit, integration, contract, end-to-end, property-based, failure injection, migration, security, load, and concurrency testing, along with test isolation, deterministic fixtures, and production-like environments. Question 18. How would you investigate and fix a memory leak in a production backend service? First, I would distinguish a leak from legitimate cache growth or garbage collection pressure using memory graphs, heap size, GC pauses, and restart patterns. I would capture heap profiles or allocation traces, compare retained objects over time, and correlate them with endpoints, tenants, and recent changes. A temporary mitigation might be reducing cache limits or recycling instances gradually. After identifying the retention path, I would add a focused test, deploy cautiously, and verify stable memory under representative load. Focus on confirming sustained memory growth, garbage collection behavior, heap profiles, allocation sites, object retention, traffic correlation, safe reproduction, mitigation, deployment strategy, and regression monitoring after the fix. Question 19. Describe how you would respond to a production incident affecting customer API requests. I would declare the incident, quantify affected requests and customers, and assign an incident commander, communications owner, and technical investigators. The immediate goal is mitigation. Roll back a change, shift traffic, disable a feature, or add capacity. I would communicate impact and updates honestly through the appropriate channels while preserving logs and timelines. After recovery, validate error rates and customer workflows, then hold a blameless review focused on contributing conditions, detection gaps, and owners with deadlines. Be sure to mention incident severity, customer impact, communication, mitigation before root cause, role assignment, timelines, rollback, evidence preservation, recovery validation, and a blameless postmortem with concrete corrective actions. Question 20. Tell me about a backend engineering trade-off you made and how you evaluated it. In one service, I chose asynchronous processing instead of making users wait for a long synchronous request. The trade-off was better reliability during spikes and lower request latency, but users needed operation status and eventual consistency. I compared queue throughput, failure recovery, implementation cost, and customer workflow requirements before deciding. We returned an operation ID, added polling and webhooks, and measured completion time and support tickets. The result was more resilient, though I retained synchronous execution for small, predictable operations. In your answer, present the context, constraints, alternatives, measurable criteria, customer and operational impact, implementation, results, and what you would change, demonstrating ownership and pragmatic engineering judgment. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.